So we're going to start talking today about kind of the next stage in our convection thought process, which is turbulence. What we've done so far, we've talked about just laminar flow. And in laminar flow, you have flow that's coming over a plate or some surface, and it's interacting with that surface. And you start having this shearing of fluid, right? So it's kind of intuitive to think about, laminar flow, where it's just things are just moving in a very ordered, steady way. But turbulent flow, as you probably know, is nothing like that. Right? Now we introduce bulk fluid motion in the direction that's normal to the surface. Right? We're starting to see, just due to the instability of the flow, we're seeing vertical movement away from the plate. And so that really fundamentally changes the properties of the flow and kind of the behavior. So we're gonna talk through some of the concepts here. We might, in fact, get to, if we get through this fast enough, we might start talking about Reynolds average equations, which are a method for actually solving this, and it's something that we haven't done, we didn't do in previous classes. So okay, so starting with this idea for laminar flow, let's just kind of think about what the transition from laminar to turbulence is going to look like and the conditions under which that would happen. So let's say we'll start out and sketch our boundary layer again. This is flow coming in this direction at U infinity, say T infinity as well. And we know now, having done our laminar analysis, that at this leading edge, you start to get the growth of a boundary layer, right? And that's going to look something like this. You can get this boundary layer that's growing. You can get both a thermal boundary layer if there's a, TS is different from T infinity, and you'd also always get a momentum boundary layer forming. So that's happening. And at the same time, if we were to, so we'll call this delta M. At the same time, if we were to plot the shear stress of this situation, right, shear stress is a function of position X. Here's our position X. What would we see? Well, right at the leading edge, we have a very thin boundary layer, and so there has to be a really steep gradient in velocity right at the leading edge. So shear stress is, well, effectively infinite at the leading edge, and then you get it trailing off as you move in the positive X direction like this. All right, so this is our tau S as a function of position. So if we think a little bit about this, what we're seeing here is tau S is the definition of that was what? Mu partial of U with respect to Y evaluated at Y equals 0. Okay, we approximate that as saying it's mu times the biggest du possible, which is U infinity, divided by dy, which is what? Delta M. So that's our approximate model of shear stress. So now you can look at this and you can see at some point, you're going to start, as you continue to increase in the X position, your delta M continues to grow, your shear stress is going to go down. So if we remember, there's this definition of Reynolds number. Okay, so Reynolds number is defined as some U characteristic, some characteristic velocity times L characteristic times rho divided by mu. And this is proportional to, right? Not exactly equal to, but proportional to, which is that symbol there, the inertial force, or inertial, we'll call it inertial terms, divided by the viscous terms. Right? Meaning, if I were to characterize how much viscous force is present in the flow, in the boundary layer, and characterize the inertial force present in the boundary layer, and take the ratio of those two things, that's my Reynolds number. So if we think about this, at some point, as we continue to go out in X, and that shear stress is changing, my viscous force is decreasing, the Reynolds number is going to eventually get to a point where the inertial part of the flow is really dominating over any kind of shear stress. And in that situation, the flow can become unstable, right? The inertial, any slight change in inertia is not muted, basically, or it's not suppressed by the viscous shear, and it just causes these eddies and disturbances in the flow to start forming. Okay, so just carrying this out, we're going to say our inertial term is approximately rho u infinity squared. Our viscous term is approximately, what did I write up there, mu times u infinity over delta m. So then our approximate Reynolds is going to be, Reynolds is approximately rho u infinity squared delta, sorry, it's a u infinity squared delta m divided by mu times u infinity, right? Which of course is, that's our Reynolds number basically. But one thing that we're noticing here is I'm defining this now just for the sake of discussion in terms of delta m. Typically when we're talking about a characteristic length or characteristic dimension, that is going to be for a flat plate, that's position x. Or for a internal flow, when we get to that, that's going to be like the diameter, hydraulic diameter, something like that. Really what we care about though is this ratio of inertial to viscous forces. And the way to characterize that is really most accurately in terms of the boundary layer thickness. Okay. So we're going to go through a little bit further here and we'll say now Reynolds delta m. So you'll notice I'm going to start writing, we've been a little sloppy about when we're writing Reynolds, how we actually write it out. I'm going to try to be careful here and say Reynolds in terms of the characteristic length. So Reynolds delta m is my Reynolds defined in terms of my characteristic length being delta m, as opposed to say Reynolds x or Reynolds L, right, which is a characteristic length in terms of x or L. Okay, so here now with this, we have Reynolds delta m, okay, is approximately rho u infinity delta m over mu. And if we define it this way for flow over a flat plate, it turns out that the critical Reynolds number where the inertial forces are so large that it becomes unstable is actually approximately equal to 3,500. All right. Now, if you remember taking heat transfer fluids, right, this is maybe a little surprising because we're talking about external flow over a flat plate, and you might remember the number 5e to the 5th. That's kind of our critical transition. Well, the only difference here is I'm defining this in terms of delta m, not in terms of x. So if we define it in terms of the boundary layer thickness, it's 3,500. And this is actually a more universal definition, a more universal number. And it's sort of not coincidental that this is really close to the critical number for internal flow, which you might remember is like 2,300. All right, so this is about the point at which you're going to start transitioning in your flow. Okay, so then let's just kind of sketch out what it looks like when we transition and get to some definitions here. All right, so let's sketch our plate again here. We have flow coming in, u infinity, t infinity, and position x here, and then this is position y. So we start off with a laminar boundary layer. And at some point, we're going to say our RE critical is going to be rho u infinity delta m critical. That's the thickness of the boundary layer at which that 3,500 is exceeded over mu. Right, that critical we just said was 3,500. So if I solve this, what I want to do is solve for the critical boundary layer thickness delta m critical. So let's do that, just algebra, right? So delta m critical is going to be equal to, solving that, just mu divided by rho u infinity times the Reynolds number at delta m critical, which is 3,500. Okay, so we have this expression now for delta m critical, and then that's going to correspond to, let's say, this thickness here, right? So this thickness here being delta m critical. Okay, so once you get to that point, we actually enter this transition region. Normally, when we're drawing this out, we just draw it as a sudden transition. So you start getting this unsteady flow, and it'll grow, more rapidly. And what we're seeing here is that, yeah, you're starting to see chaotic movement in the fluid. It's sort of cycling, you get these eddies. And so this boundary layer no longer grows nicely by this diffusion process. It's growing by a chaotic process. So on average, it's growing more quickly. If you look at any sort of local position, it's very chaotic and unstable. But okay, so you're growing. So we go from laminar here to turbulent here. So then, all right, so let's figure out how do we get to that normal, the kind of well-known number, 5e to the 5th. So let's use our definition up here, delta M critical, and then let's try to relate it to the current definition, or the previously understood definition of Reynolds number in terms of X. So if we say here that this boundary layer, we're going to use our self-similar solution, which is delta M over X is equal to 4.916 divided by square root of Reynolds in terms of X, right? That's our definition, or the boundary layer thickness equation using the self-similar solution, which is an exact solution. So we'll use this in combination with our other definition to solve for the relationship between the two things. So let's do that. Let's write out Reynolds in terms of delta M is equal to rho u infinity delta M divided by mu. Okay, so now we have an equation here for delta M. So delta M is, let's rewrite this. So it's rho u infinity over mu times our delta M, which is 4.916 over the square root of Reynolds X. And then we do need an X in the numerator as well. Okay, so we just substituted delta M into that equation. So now we just have to do a little bit of algebra to rearrange this. So let's see, let's write out the Reynolds number, which is, so this is 4.916x divided by the square root of rho u infinity x over mu, right? Again, Reynolds in terms of x in the denominator there. Okay, a little bit more algebra. So what we want to do is simplify this down. So we see that there's, oops, sorry, I'm missing the stuff that comes along. So we had rho u infinity over mu coming along as well, right? So now we want to, we've got rho u infinity mu appearing in two places. So let's simplify that. Let's take that stuff, rho u infinity mu, and bring it inside the square root. If we do that, we end up with, let's see, 4.916. Let's also bring x inside. So if we do all that, we end up with, let's see, we had rho originally. So we bring the other rho in, that's rho squared in the denominator. We have u already in here, u infinity already in here. Bring the other one in, that's u infinity squared. Mu as mu squared in the denominator, divided by mu, and then x over x squared. There you go. So all we're doing is just bringing stuff inside. So then we cancel a bunch of stuff out. And this gives us what? Reynolds in terms of x is equal to 0. Let's see. Oops. No. Let me do it this way. Reynolds in terms of delta M, which is what we're doing, is then equal to 4.916. And all of that just becomes, that whole thing in the denominator just becomes Reynolds square root of Reynolds x in the numerator. Hopefully you can see that. So we have 1 over square root of Reynolds here, square root of 1 over Reynolds x in the denominator, that goes in the numerator. So then let's solve that last equation in terms of Reynolds x. And we see what? So then we see Reynolds x is equal to 0.041 times Reynolds delta M squared. Okay, now we know that Reynolds delta M, the critical Reynolds delta M there was 3,500. So let's substitute that in, and then we end up with Reynolds at X critical is going to be 0.41 times 3,500 squared. And voila, that equals 5 times 10 to the 5th. Okay. So that's the relationship between the number you're familiar with, 5e to the 5th, and the boundary layer thickness. Questions on that? Okay. So, it's kind of interesting how those things are related to each other, but it is important that, really when we're defining things in terms of a critical length or a length in general, some characteristic length X, that's just a convenience for us, right? Defining it in terms of X is convenient because we know X. We can look at the position of the plate. But there's always a translation between that position or the Reynolds number defined by that position and the thing we actually care about, which is the boundary layer thickness, okay? So let's look then at velocity profiles, just trying to continue to develop our understanding here.